Hi guys, today I wanted to talk to you about low pass filters. So let's start with a simple RC. This is the output voltage and this is the input voltage. So the first thing that you want to know is how to study it, and in order to do that you have to go in the Laplace domain and to study the ratio V out over V in, which is also called h of s transfer function. You have to treat the capacitor like a resistor with a value 1 over Sc. And if it, so the capacitor becomes a resistor in the Laplace domain with the value 1 over Sc, and the inductor becomes S times L. So as you may know, if you put a capacitor inductor, you're introducing a pole or a zero based on the configuration. You're introducing basically an order in your system. So if you do the calculation, I already made it for you, you have the typical divider, so 1 over Sc over 1 over Sc plus R, and if you complete the calculation, you will obtain 1 plus S R C. And you expect a response like that with minus RC, 1 over 2 pi RC here. So I put on Ltspice already the filter here with 1 kilo and 10 micro, and I put already the Laplace transformation here. So to do this, remember to put E1 and to write exalted sentence. So as you may know, this result here, out 1, and the result here, out 2, should be equal, because I'm basically saying that I don't know what type of filter is this, but I'm giving you the transfer function here. And it should be the same. So if you now do this, you see that out 1 is attenuated. There is also a bit of lag because it is introduced by the filter. And if you do it out 2, you see that out 1 and out 2 are exactly the same. Yeah, there is of course, a little bit of difference, but this is of course, the transformation. Maybe because here there is an ESR which is automatically introduced, but by the way, this is how it should look. So if you wanted to study low-pass filtering, the first thing that you want to know is to do this, to see how much the signal is attenuated with a sign. For my mistake, I put just 100, but let's put just 1. So if you have 1 volt, you're gonna have basically the half with this configuration. Do you have to do this every time to check the Laplace transformation? The answer is no. You have just to, we can cut off this guy. You have just to insert basically a voltage here, and instead of performing the ADC analysis, you perform the AC analysis, and just write type of width decade, 100 point for decade, 1 and 1 megahertz. And as you can see, this is the ideal response of the low-pass filter. If you check the transformation, if you check the response at minus 3 dB, it is 50 Hz. How can you check that? Well, just do the formula, 1 over 2 pi times R times C. Well, you can even add, if you don't want, if you are too lazy to open MATLAB, you can, or Excel, you can just write here V equal to 1 over 2 times 3.14 times R times C Of course, it's not gonna work. No, maybe it is. Maybe it is still gonna work. Never try that. Okay, so as you can see, as a result, I obtained 15.94, which are not volts in this case, but it is just a way to check the cutoff frequency, which is a 15 hertz. So this is just this was just for my own curiosity. Now I will explain to you the other types of filters. So let's go on. You may want to design if it is active or non-active, it doesn't matter. Remember that the difference that the active filter has the op-amp and it should be supplied. So as you can see, there are different type of filters. The Bessel, the Butterworth, the Chebyshev, the Elliptic, and so on. So what are the differences and the advantages of this? So as you can see, this is called the passband. In red, this is called the passband. Now, this type of filters have different application. I would say that the Bessel, the Bessel, and the Butterworth, these two have the flat passband. As I reported here in the table, the Butterworth has a smooth curve and has no ripple in the passband, as it has the Bessel. You should use these two type of filters, as you can see here. Butterworth. Okay, I forgot to put the Bessel, but you should use these two type of filters. For instance, whenever you want to read, let me explain an example. You want to read the you for instance have a buck converter. Now you put a divider at the input, but since the circuit is switching at, for instance, 0.5 MHz, if you just read the input signal in the input voltage like this, you will have, as a result, not a DC signal, but you will have some ripple overlapped to your DC signal, owing to the fact that your circuit is very noisy. And so you should design a filter to cut off this 40 kHz ripple, and this filter should be a Bessel or a Butterworth, since you have a flat passband, so you don't have any kind of increase, and a smooth attenuation. So you should have, for instance, minus 40 dBs at 0.5 MHz, so that this ripple is attenuated. This is an example. So Bessel and Butterworth are most used in measurement application. Now let's talk about the Elliptic and the Chebyshev. As you can see, the Elliptic and the Chebyshev have this kind of ripple in the passband. So what does it mean? It means basically that in your whenever you're gonna read your signal here, if you use this kind of filters for measurement, it's gonna be a problem if the passband is too high, because if you have, for instance, 1 kHz of a signal with some ripple at megahertz, noise at megahertz, the signal at 1 kHz can be either attenuated or either amplified a bit. And if you want a precise measurement, you honestly don't want that. So the elliptic, for instance, it is used in mostly in RF application, because the elliptic, let me draw something here. The elliptic has this kind of attenuation here, which gives a high attenuation in this point. So for instance, if you have a circuit with an antenna, the antenna is gonna have, for instance, 8 megahertz, but at 2 times that frequency, or even 3 that frequency here, you're gonna have some spurious harmonics that you want to cut. And if you're able to design a filter which is able to cut the second harmonic, the third harmonic, the fourth harmonic, you don't care about that here it is attenuating less than this point here, because you want a filter which is exactly attenuating the second and third harmonic. So I can give you an example of RF tool. If you have the elliptic and you use the cutoff frequency, for instance, of 1632 megahertz, you put also an elliptic of 6th order, low pass type, and you compute it. As you can see, you have to check the blue curve. As you can see, the elliptic is cutting exactly. Of course, it should be designed, but as you can see, the elliptic is cutting exactly where I should want it in the first, in the second, third harmonic, and so on. So elliptic filters are specifically designed, for instance, for RF to cut the harmonics of the filter, or even for the matching. If you do happen to also to design the Butterworth, the attenuation is very smooth, and the flat band is it has no ripple. If you do instead the Chebyshev, the higher the order. Oh, very well. This is very attenuated because I put the passband ripple of 0.10, but in reality is way higher than you can imagine. So let me put 1 dB, because this is what you're gonna get. And the higher the order, the higher will be the oscillation. So as you can see, this is a 10 order Chebyshev filter, and the oscillation is very high. So even though you wrote 1 dB as passband filter, it's gonna oscillating very, very high. Even if you write 0.1, this oscillation is not gonna change. So remember that the higher the order, so you see, even though I designed a filter which has less attenuation than before, the resonance and the oscillation remains the same, even though the amplitude is attenuated. And this is not very good if you want to read or to make the signal pass here, because it can be either attenuated or either amplified, and honestly, you don't want that. So let me put as an example this filter here. Okay, so as I was saying before, the higher the order and the higher the attenuation. As you can see, this is the first order, second order, third order. But since this is a Butterworth response, the flatness is always should be always flat. But for the elliptic and for the Chebyshev, remember that the higher the order, and the higher is gonna be this oscillation here. I reported everything in this table, so you can have a look at it. As you can see, the disadvantages of the Chebyshev is the ripple in the stopband path, even for the type 1 and the type 2, and also for the elliptic. Elliptic also requires a large number of components, as you saw before. Now remember that this is the 10 order Chebyshev, but if you put the elliptic low pass, it's gonna be a nightmare. So as you can see, there is a very number of components. If you want a band pass, it is way worse, because you need even more components to guarantee the both the high and the low pass attenuation. And as you can see, it becomes impossible. This is basically a train of components, so you can't design something like that. And attenuation is and you can't even distinguish the attenuation for. So what is this? It is impossible to design something like that. So let me put the inactive. Let me put the this circuit here on Ltspice. By the way, this is a third order Butterworth filter, so I will also teach you how to simulate this kind of active filters. So let me close this, and let me copy this filter. So R1. Now we need R2. This is 10 kilo, 10 kilo. C equal to 0.31 micro. Is this correct? R32. Let me put exact components. Okay, let me put the op-amp. Never use this op-amp here. Always use universal op-amp 2. Okay. 1K, 1K, 1 kilo, 1 kilo. So this is the feedback with 1 kilo and 1 kilo. And this is all connected here to here with a capacitor. With the same value here. And this is connected here. And just a low pass at the end. So this is composed by a second order cell. Now the first thing that you want to do is to also put the power supply. So let me put 50 volts. Let me call VCC plus, and the same for the minus 50 volts VCC minus. And let me put it here and here. I don't like overlapping. And let me put AC1. Okay, so now let's simulate the response. Decade 100, 1 Hertz, 1 GHz. And this is the response of the filter. It has a let me put okay, so now it is okay. So now you can see it better. So this is the passband, and this is the response of the filter. Now you may wonder why it is going on like this. Well, the fact is that there are also some non-idealities in this circuit here, and so you should also take into account for that. This is the second order cell, and the op-amp is so the problem here, the problem with this kind of filters is that also the response of the op-amp. As you can see, the op-amp is not more attenuating from that point onwards, and so you should also consider the fact that this op-amp here should have also high bandwidth in order to make the active filter work. In the next video, I will show you how to simulate this kind of filters in Ltspice, because this is for RF electronics, and you have to know what is S21 and S11, S21, and all these things here, the S parameters and so on. Because LPF for RF electronics changes a bit. It's not so different, but it changes a bit. Thank you for your attention, guys, and see you in the next video.